Hi all. In this video we are going to see one important question from signals and systems, that is, explain ideal LPF, HPF, BPF and BRF with graphical representation. Okay, what is LPF, what is HPF, what is BPF, what is BRF? Okay, if you are already studied signals and systems, you might have idea. If you are new to that topic, don't worry, I'll tell you. LPF means low pass filter, HPF means high pass filter, BPF means band pass filter, BRF means band rejection filter. Okay, or we also call band stop filter. Okay, BSF as well. You can call band stop filter or band rejection filter. Okay, so we'll see one by one. What is low PF, LPF? So LPF means low pass filter. Low pass filter. Definition first you need to write. What is definition? Low pass filter is nothing but it allows, you can write simple definition, no worries. It allows all frequency component, all frequency components which are less than the cutoff frequency. Cutoff frequency. For example, if we take omega c as the cutoff frequency, so the filter will allow all the frequency components which are less than omega c. So first we will write the, will represent the graphical representation is, so first you take x-axis is frequency, so that is omega, and y-axis is our h of omega. So the graph between omega and h of omega is called the graphical representation of low pass filter, that is called characteristic graph. So how to draw the graph of low pass filter now? So here omega is called frequency component. If you don't know, just I'll write here, no worries. Frequency component. H of omega is called transfer function. Okay, transfer function. H of omega is called transfer function. First time you write for HPF, BPF, BRF, no need to write. Once you write, it's enough. So it allows all frequency components which are less than the cutoff frequency. So that means, for example, take omega c as the cutoff frequency for this low pass filter. I'm taking omega c. So obviously I will have minus omega c here. All frequencies which are less than the cutoff frequencies, means from here to it is omega c, assume like this. So all frequencies which are less than omega c, so it will allow this component, and minus omega c, less than minus omega c, so it will allow all these components, it will allow. So this is called, this band is called pass band. You represent pass band. What is this called? Pass band. So remaining this and this is called stop band. This is stop band, this is also stop band. So from this, how to write the equation? You can write the equation h of omega is equal to 1 when the frequency component 1 when omega is less than omega c, 0 otherwise, or else you can mention omega is greater than omega, modulus of omega is greater than omega c. Omega c is nothing but cutoff frequency here, right? Cutoff frequency 0 otherwise, you simply write 0 otherwise is just greater than. Okay, write like that. Okay, omega is less than or equal to omega c, you can mention. Okay, so this is the definition of low pass filter and graph, and this is the equation representation. Okay, set representation. This is graphical representation. So what about high pass filter? High pass filter means simple, it is quite opposite to low pass filter. I'll tell you what is high pass filter. HPF means high pass filter. Okay, what is the definition? Definition, it allows all frequency components which are more than or higher than cutoff frequency. Here cutoff frequency I'll represent as omega c. So, and rejects all frequency components which are less than the cutoff frequency. Okay, so the graph representation, what is the graph representation? Graph representation is between omega and h of omega. What is h of omega? Transfer function. What is omega? Frequency. So this is x-axis, this is y-axis. So how the graph looks like? So for example, if we take omega c is here, so I'm taking omega c is here. Okay, this is omega c, this component will become minus omega c. So what this HPF will do now, above omega c it will allow, so it will allow all these components. Okay, above omega c it will allow, this is called pass band. Now this is called pass band, this is called pass band. Below omega c, from here to here, it is stop band, it is also stop band. So this is called stop band. So how will be the equation? H of omega is equal to 1 when omega value is greater than omega c, 0 otherwise. Okay, this is called HPF or equational representation. This is graphical representation and this is the definition. Okay, this is called high pass filter. For example, if you take, I'll tell you, for example, if it is given like a ideal high pass filter, 2 mark questions may ask, having cutoff frequency omega c is equal to 10 kilohertz, represent graphically అన్నాడు అనుకోండి. So if you ask the question like this, then what you will do, this is omega, this is h of omega. You no need to write this answer in this question. Okay, this is for 2 marks, I'm just explaining you. Okay, so omega c how much? 10. So 0 1 2 3 like that, so I'll take 10 here. So this is our omega c and this is our minus 10, this is our minus omega c, it will become minus omega c. So how will be the graph? It is high pass filter, so all frequency components more than 10, all frequency components more than 10. So it is pass band, it is pass band, this is stop band, like this. Okay, it will come for 2 marks, not for long answer question. So you just need to know what is high pass filter definition, how the graph represents, what is the equation. So what is our next question? Next one is band pass filter. So what is band pass filter? I'll tell you. Band pass filter. Okay, it allows all frequency components within the given range. So here we will be given two frequencies, not single frequency. In low pass filter and high pass filter, we use it to give single frequency, that is cutoff frequency. Here we use it to give two frequencies, omega 1 and omega 2. So in between the range it will allows. Okay, so and suppress or reject or attenuate, you can use anything, attenuate all frequency components. So my handwriting is not good, so just try to understand, which are other than the given range. So how is the graph looks like? So same story, omega, h of omega. So here we will give two frequency components, one is omega 1, and for example they are given range is in between omega 2. So here we will get minus omega 1 minus omega 2. So it will allow all frequency components within the given range, that means omega 1 to omega 2 it will allow, same like minus omega 1 to minus omega 2 it will allow. So this is pass band, this is also pass band, and remaining all are stop band. This is stop band, so I may represent with vertical lines, so you will understand. So this is pass band, this is pass band, and this is stop band, this is also stop band, this is also stop band, this is also stop band. Only in between the range it will allow. So how will be the characteristic equation looks like? 1 when our omega is in between omega 1 and omega 2. 0 you can mention otherwise. Okay, this will be the equation. In between the range it will allows, in between the range it will allows, other than that it will suppress. So for example, if the omega 1 value is 10, omega 2 is given like 12, so how will be the graph looks like? You can take 10 here, 12 here, so the graph is like 10 to 12 it is pass band. Here also minus 10 minus 12, this is pass band, this is pass band, this is pass band. You can write pass band, pass band. Remaining all things are stop band. This is stop band, this is stop band, this is stop band, like this. Okay, band rejection filter. Okay, fine, last one, band stop filter or band rejection filter. Okay, band rejection filter. What is band stop or band rejection filter? It allows, okay, all frequency components which are other than the given frequency range and attenuate all frequency components which are within the given range. So this is the definition. Sorry. So how will be the graph looks like? Same omega and transfer function h of omega. So for example, they have given omega 1 and omega 2. So same like minus omega 1 here, minus omega 2. So in between omega 1 to omega 2, it will suppress. So this component and this component. This is stop band now. This is stop band. This is called stop band. In between the range, it will stop. This is called stop band. And it will pass all frequency components through it other than the this given range. So this is called, this and all called pass band, and this is also called pass band. Okay, this is also called pass band. Pass band, pass band, pass band. This is also pass band. How will be the characteristic equation then? H of omega is equal to 0 when omega 1 less than or equal to modulus of omega is less than omega 2. 1 otherwise. Okay, this is the characteristic equation like this. Okay, say just opposite to band pass filter. So if we given like omega 1 is equal to 10, omega 2 is equal to 12. So same, draw the graph. This is 10, this is 12. So it will suppress this. It will suppress minus 10 to minus 12 and allows all these frequency components. So you should not mention like this. You can mention this and this and this. You can leave this spot, like I'll show you. For example, no need to write example for your information. Okay, omega 1 value 10, omega 2 value some 13 he given. So BRF file, right? Omega, it is minus, okay, minus omega, let it be h of omega for band rejection filter. So omega 1 how much? 10. So it is 10, it is 13, minus 10 minus 13 if you say. So all frequency components other than that this range, so it will allow this, it will also allow this. So just take like this, and it will also this range it will not allow, so it will allow from here. This will be the ideal graph. Okay, thank you.